Today we're going to be talking about how logarithmic functions and exponential functions are inverses of each other, and then we're going to be graphing some logarithmic functions. So this first page here, we're going to be skipping around on it and not doing a lot, but there is something that we do need to talk about, and it's because that logarithmic functions and exponential functions are inverses of each other that we can use these properties. So remember, g of f of x means you're going to take f of x and plug it into the x of g. So that would really be log base b, but instead of x, we would write b to the x power. But we also know that when you do the composition of inverse functions that it just equals x. So generally, we can make this assumption that when we have log base b of b, where those two things match, you can just simplify all that to whatever this exponent is. And we haven't seen that before. We've seen log base b of a number equals something, but we have not seen log base b of b raised to the x power. We will see that down here a little bit. Conversely, we could take all of g and plug it into the x of f, and that would look like this. You'd have b raised to the x power, but instead of it being x, it would be this whole g equation up here, log base b of x. And again, we know that when two inverses are composed, that it just equals x. So down here, we'll just see how this is useful in some instances, but we're not going to really spend a lot of time on here because this is not something that we're going to use all that frequently. So we know that when there's no number written for the base, it's a divisible base 10. So we have 10 raised to the log base 10 power of 7x. So this would just equal 7x. Same thing over here, invisible 10. So 10 raised to the log base 10 power of 7.6 would just be, 6.7 would be 6.7. Now here's where it gets a little bit more difficult. We'll do these two over here and then move on. What we see is that we have log base 3 of 27 raised to the x power, but we don't have the same thing here. We have 3 and 27. We could change 27 to 3 to the third power. So we could say log base 3 of 3. And remember, when you have a power raised to a power, you multiply, so it'd be 3x. Okay, well, we know that when we have log base b of b, that your answer or your simplification is just that exponent. So this is going to be 3x. We know that ln is log base e, so this is just going to equal 5x, your exponent right here. Now on the next page here, we're going to be calculating inverses. And remember, when we did inverses before, we switched x and y, and then we would try to get y by itself. The same idea is going to happen here. We're going to switch where x and y are, but remember, when you're working with word problems, we don't do that because we also change the meaning of the word problem when we do that. So we're going to switch x and y, but we have to get the log or the power, the base being raised to the power alone. Then we switch from log to exponents or exponents to log, and then get y by itself. So we have to do that switch that we talked about the other day. So find the inverse of the function. So let's switch x and y. So x equals log of 3/2, log base 3/2 of y. Right. Now that we have the log by itself, and then we say, well, the word log isn't by itself. No, this whole thing is attached to the log. When we say log by itself, we say that we mean that there's no number out in front, or that we're not adding a number on the outside. That's what we're referring to when we're talking about getting the log by itself. This log is by itself. So now we switch it to exponent form. And we haven't really done this. We haven't really gone. Now we're going to go to exponent form from this log form. Our base is 3 over 2. And remember, we say that log equals exponent, so the word log is on the opposite side of the exponent, making this x our exponent. And then this equals our other number, y. Well, y is now by itself, so this means that the inverse of y is 3 over 2 raised to the x power. Oops. All right, now in part B, first thing I'm going to do is I'm going to switch x and y, but I'm also going to change this to log base e. And the reason for that is because when we go to exponent form, it's easier to see what we're going to do. Log is not by itself, so we subtract 5 from both sides, giving us x minus 5 equals log base e of y minus 4. E is our base. Our exponent is this whole thing, x minus 5, and this is going to equal the other number, y minus 4. Y is still not by itself, so we're going to have to add 4 to both sides. Now that 4 does not get added to the exponent. This is going to be e raised to the x minus 5 power plus 4 equals y. And then we would end with writing that in inverse notation. E to the x minus 5 power plus 4. A couple of mistakes that students will most likely make is adding the 4 to this exponent up here. Nope, they're separate things. Or right here, trying to add 4 before changing it to exponent form. If it's in the parenthesis, we can't touch it. Only things outside the parentheses can we touch. Now, letter C is a bit different because we're going from exponent form to log form, and we haven't done a lot of that. So first, what I like to do is I like to write the word log because we know we're going to log form. So we have x equals 7 raised to the 2y power. So log, what number is being raised to the power? Well, that's 7, so it's log base 7. And we know logs equal exponents, so this is going to equal 2y because that is our exponent. And then that this x goes with the log, the other number. Well, now we just have to divide both sides by 2. So this is going to be log base 7 of x over 2 equals y. And then we can write that in inverse notation. The inverse of y is equal to log base 7 of x over 2. So what I want you to do is I want you to try these problems down here. And then once you are done, unpause it, and you can see my answers and the work on how I got it. And hopefully, if you made any mistakes, be able to fix those. All right, so I'm going to go through each one of these quickly to point out some key characteristics and maybe some areas where you might have messed up. Letter A, hopefully was not too difficult, is once your log was already by itself, once you switch it to exponent form, then when you subtracted 1 from both sides, you got y by itself. So I'm hoping that one wasn't too difficult. letter B, again, I'm hoping that wasn't too difficult, and you may see, why do I have parentheses around the x down here and down here? Well, notice in the pink line that this is all by itself, and this is y minus 4 on the right side. And we want to be able to differentiate between what I want, which is what I have down here in red, versus what we had up here, this x minus 4 in parentheses. It can be unclear if I were to leave it like this. If I were to leave it as log base 5 of x plus 4, it can be a little bit confusing on, is this x plus 4 together? Or is it x and then plus 4? Because we know those can mean totally different things. If we talk about a graph, and we're going to get there shortly, this would mean a horizontal shift to the left 4 units, whereas this would mean a vertical shift 4 units. So that's why I put parentheses around the x, just so that it's clear. With this one, hopefully you were able to make it at least down to this step. Then once you change this to a log, notice that the x minus 7 is by itself over on that left side. So that means it needed to go in parentheses once we change it to a log. And then lastly, I changed log base e to ln. You always want to do that. It's just more mathematically correct. Now, when we graph logs, we're going to be able to take advantage that logs and exponentials are inverse functions of each other. And remember, if they're inverses, that means they reflect over the line y equals x. That means that your domain and range switch. Now remember, with exponential functions, our domain was negative infinity, comma infinity. Our range was, 0, comma infinity, unless we had some transformations. And we had an asymptote at y equals, in this case, 0. Now, if we're switching the x and y, because these are inverses of each other, what that means is that your domain is now 0, comma infinity. And your range is now negative infinity, comma infinity. And instead of your asymptote being y equals 0, it is x equals 0. So we're using that idea of inverses to help us build background knowledge for logarithmic functions. And our table, when we construct the table, we're going to use the same ordered pair, but switch them. Now let's look at the next page to see what we're talking about. Because remember, for exponential functions, the table was 0, comma 1, and then 1, comma b were our 2 points. You see that they've switched. And like I was saying, our a, h, and k are back, and they still do the exact same thing as they've always done. So let's graph a couple of these, and then I'm going to leave you guys to graph a few. Y equals log of 2x. So our a value is an invisible 1 out in front. Our b value is our base of the log, which is 2. Our h value in this problem is 0, and our k value is 0. Our asymptote is x equals 0. Our domain is going to be 0, comma infinity, and our range is going to be negative infinity, comma infinity. So this is going to be different because this is we've only had 2 functions that have had a domain that wasn't negative infinity and comma infinity. This is one of them. Notice x equals 0, our h is 0, our domain is 0. All those go together. So when we shift left and right, all of those are going to change with it. All right, now for our table, like I was saying up above, we're going to have 1, comma 0, and then b, comma 1. Our b value here is 2, so 2, 1. And then we would have that third row for a times y. In this case, it is just 1. And then we graph these points. So we have 1, 0, and then 2, 1. So our logarithmic graph would look like this. And our asymptote is at x equals 0. So we draw that asymptote. Now I'm going to do this one down here, and then I'm going to have you try both of these over here. Our a value is an invisible 1. Our b value is 3. Our h value is the opposite of that, so 1. And our k value is positive 2. Our asymptote is going to be at x equals 1, that k value. Our domain is going to be 1, infinity. And then our range is always going to be -infinity, infinity. Now our table, x, y, we have 0, 1, and then base 3, 1, 0, and 3, 1. So 1, 0, 3, 1. But we're going to move each point right 1, and up 2. So right 1 and up 2. Right 1 and up 2. And our asymptote is at x equals 1. So here's x equals 1. There's our asymptote. So then our graph looks like that. So just trust in the process. You do know all of this stuff. This is nothing really new. You know how to make this table. It's the same table as exponents. You just flip them. Our asymptote is now vertical, and we've done vertical asymptotes before in the rational functions. So just because this isn't exactly what we've done before doesn't mean you are unable to do it. Just stop, slow down, think a little bit, and you'll be able to try the other two. So pause the video, try the other two. When you're done, you can compare your answers to mine. All right, so here is the graph for the first one. Notice how the shape looks a little bit different than our other one. That is because of this 1/3. So it's okay that your graph looks like this. And then down here is a different base, a base of 1/2, and then we are shifted down 3. So this is what your graph will look like. So that's why I was saying this A, H, and K stuff is always going to be with us, and they always do the exact same thing in all of these. So the sooner that you understand how A, H, and K go together, the easier all this graphing will become. So thanks for watching this video. Make sure to like it and subscribe.